Modern dogfights are changing, and the era of the invincible missile is being replaced by high-power lasers that melt steel in seconds. But Sweden has a secret weapon that makes these directed energy threats obsolete. Discover how Saab is using graphene-infused armor to turn the 6th-gen fighter into an untouchable ghost. Graphene is 200 times stronger than steel, but its real power lies in how it handles heat. By integrating this wonder material into 6th-generation airframes, Swedish engineers have created a thermal shield that dissipates laser energy instantly. This isn't just passive plating, it's an active electronic evolution for NATO's northern flank. Forget everything you know about traditional stealth, because the next generation of air superiority is all about survivability against light-speed weapons. While others struggle with heat management, Sweden's newest jet uses a graphene skin to neutralize high-power lasers on impact. It's the ultimate shield, transforming a fighter jet into a flying lightning rod.
Look at the Baltic theater in 2026 and you can feel the air war changing shape, not because dogfights have disappeared and not because missiles no longer matter, but because the battlefield is filling up with a new question. What happens when defense fires back at the speed of light? Across Europe, militaries are rushing to build layered counter-drone shields on the eastern flank. NATO deployments around the Baltic are adapting to the drone threat. The EU is pushing its so-called drone wall concept from the Baltic to the Black Sea, and major European laser programs are moving from lab prestige to operational planning. In that kind of environment, the old logic of survivability starts to crack. Flares and chaff still matter against heat seekers and radar-guided missiles, but against a precision beam, they are not the main answer. A laser does not need to be fooled the same way a missile seeker does. It needs line of sight, dwell time, power, and tracking stability. That is a very different fight. And this is where the physics turn nasty. High-energy laser damage is not Hollywood fireball damage. It is thermal ablation. The beam pours energy into a tiny spot, heats the material faster than it can shed that heat, then begins to degrade resin, weaken structure, char composites, melt surfaces, and eventually punch through. In published tests, carbon fiber-reinforced polymer panels between 1 and 6 millimeters thick were exposed to continuous wave high-energy lasers at up to 10 kilowatts, and researchers found measurable perforation behavior tied directly to laser energy, material thickness, and spot size.
Another recent study on CFRP described the process as high-temperature ablation that progressively degrades thermomechanical properties. So the real danger is not just a hole. It is the silent collapse of strength, the weakening of load-bearing structure, the kind of damage that can turn a survivable aircraft into a dying aircraft before the pilot fully understands what happened. That is why Sweden's answer cannot just be a faster Gripen with better missiles. Saab and FMV are already working on continued future fighter concept studies built around manned and unmanned solutions, a system of systems approach, technology development, and demonstrators. Public reporting in early 2026 also pointed to Saab planning a fighter-sized uncrewed demonstration aircraft for 2027, ahead of a broader future fighter decision due around 2030. In other words, Sweden is not thinking only about the next airframe, it is thinking about the next combat ecosystem. And in my view, that makes perfect sense. Once air combat starts shifting from missile evasion to heat management, sensor disruption, autonomy, and distributed survivability, the winning platform will not just be the one that flies fastest, it will be the one designed from day one to survive being seen, tracked, and burned. But this is the balanced part. Lasers are powerful, not magical. Weather, range, power generation, and platform integration still limit them. So this is not the end of missiles. It is the beginning of a battlefield where beams, drones, missiles, and electronic warfare all start stacking on top of each other.
And this is where the story gets really interesting, because once lasers enter the equation, the fight is no longer only about stealth, speed, or missiles. It becomes a fight about heat. And when you start talking about heat, graphene suddenly stops sounding like science fiction and starts sounding like strategy. In ideal form, graphene's thermal conductivity has been reported above 5,000 watts per meter Kelvin, while high-purity copper at room temperature is around 397 watts per meter Kelvin. That does not mean a fighter jet can simply be wrapped in pure graphene and become laser-proof. Real aircraft materials are never that simple. But it does mean that engineers looking for ways to move heat away from a laser strike point would be forced to take graphene very seriously. In a laser age, the goal is not magic invincibility. The goal is to spread heat faster than damage can localize. The real breakthrough then is not graphene armor in the comic book sense. It is graphene integrated into composite skin systems. Recent reviews describe graphene skin materials as valuable because their continuous lattice structure and strong bonding can improve performance compared with loose flake coatings, while graphene polymer composite research shows that the key variables are filler loading, defect density, dispersion quality, layer count, and especially the creation of interconnected 3D heat conduction networks.
Manufacturing routes already under discussion across the materials world include chemical vapor deposition for large area, high-quality graphene films, along with in-situ polymerization, solution blending, and melt blending for graphene-enhanced polymers. In plain English, the idea is to build a skin that does not let the beam cook one tiny spot to failure, but instead drags that heat sideways across a broader structure before it can cut deep. That is why graphene matters to a country like Sweden. Sweden cannot afford a lumbering flying tank. Its whole air combat entity is built around agility, efficiency, survivability, and smart engineering. Graphene-reinforced polymer composites are being studied precisely because they can deliver multifunctional mechanical and thermomechanical gains at low filler loading, offering a possible route to more protection without paying the full weight penalty of simply adding thicker metal. Aerospace reviews also keep coming back to the same attraction. Graphene is exceptionally light, mechanically impressive, and potentially useful in ultra-strong yet lightweight composite structures. My view is that if Saab really wants a sixth-generation aircraft built for the laser era, then this is the material logic it cannot ignore. But the balanced reality matters too. Promising lab data is not the same as a mature fighter airframe solution. Scaling, uniformity, defects, manufacturing cost, and certification are still major obstacles. So the honest way to frame this is not that Sweden has already solved the problem, but that graphene may be one of the most credible paths towards solving it.
This is the part that changes the whole logic of survivability. A laser does not need to smash an aircraft apart like a missile. It only needs to keep pouring energy into one small point until the structure starts to fail. So the real battle is over time. Can the aircraft move that heat away fast enough before the beam burns through? That is where a graphene-enabled skin becomes so dangerous in theory, not because it makes the jet invincible, but because it can create lateral heat-spreading pathways that pull thermal energy out of the kill spot and smear it across a wider area. In plain words, the beam is trying to turn one point white hot. The material is trying to refuse that concentration. My view is that this is the most realistic way to explain the laser-proof idea. Not immunity, not science fiction, just brutally efficient delay. And in beam warfare, even a short delay can be the difference between a scorched surface and a dead aircraft. But the next layer is even more important. Once that heat is spread, the airframe itself can start behaving like a giant thermal sink. Aircraft thermal management research already treats the aircraft structure as one of the terminal heat sinks alongside atmospheric air and fuel, and newer reviews point to skin heat exchangers and ram air-assisted cooling as promising ways to reject heat. That said, this is where a balanced explanation matters. High altitude helps and hurts at the same time.
Yes, the outside air is colder, which improves temperature difference, but the air is also thinner, and that weakens convective heat transfer. One study on high-altitude aircraft heat exchangers found that after entering the stratosphere, falling air density became the dominant factor reducing the heat transfer coefficient. So the smartest script line is not that cold Baltic sky magically cools the jet, but that Sweden's future fighter could exploit a combination of structure, airflow, and ambient conditions to dump heat more effectively than a conventional airframe. And then comes the fine layer. Passive diffusion alone is probably not enough for a true sixth-generation combat aircraft. That is why this thermal battle would almost certainly have to be multi-layered. The skin spreads and delays, the structure absorbs and rejects, and the propulsion system manages the deeper thermal burden with active cooling architecture. Research on adaptive cycle engines shows exactly why this matters. Their multi-duct layouts can use cooling air for thermal management, cooling hot engine sections such as the low-pressure turbine exit, center cone wall, and nozzle expansion section, while also improving performance and infrared stealth. So if Sweden is really designing for the laser age, the winning concept is not just a stronger skin. It is a whole aircraft built around thermal discipline, where materials, airflow, and engine cooling all work together. That, in my opinion, is what makes this idea believable. Not one miracle material, but a system that treats heat itself as the enemy. Saab's public future fighter work supports that broader direction, because it is officially framed as technology development and demonstrators in a wider system of systems effort, not just a simple next airframe. But the real revolution may begin when that graphene-rich skin stops behaving like passive armor and starts behaving like an electronic surface. Not a magic shield, a smart one. Because once a skin becomes conductive enough, parts of that airframe no longer need to be dead weight. They can become apertures,
They can become sensing layers. They can become part of the aircraft's electromagnetic nervous system. Aerospace research has been moving in this direction for years through conformal load-bearing antenna structures, where RF antennas are inserted inside load-bearing aircraft laminates. And researchers now talk openly about embedded antenna arrays and even entire RF systems inside composite panels. On the graphene side, experimental work has already shown that graphene-assembled film antennas can deliver performance comparable to copper in certain antenna designs, with conductivity around 1.1 times 10 to the 6 s per meter being feasible for conductor use. So in script terms, the believable claim is not that the whole jet becomes one giant jammer overnight. It is that a future Swedish fighter could use sections of its conductive skin as distributed communications, sensing, or electronic warfare apertures without hanging more vulnerable antennas off the outside. And in my opinion, that would fit Sweden perfectly. Less drag, less clutter, more intelligence built directly into the structure. Now take that one step further. If the skin can host RF functions, it can also host awareness. That matters because laser warfare is not only about surviving heat, it is about knowing what kind of beam is hitting you, from where, and how fast you need to react. Recent laser situation awareness research has demonstrated systems that can determine incoming laser wavelength and angle across a wide field of view, with reported angle accuracy better than 0.05 degrees, wavelength accuracy around 8 nanometers, and field of view up to 120 degrees in azimuth.
More broadly, optical band electronic warfare already treats the acquisition, analysis, and processing of optical signals, including laser emissions and UV/IR signatures, as part of recognizing and countering threats on the battlefield. So the strongest script line here is that a 6th-generation smart skin could feed distributed optical and electromagnetic warning data straight into the mission computer, allowing the aircraft to trigger beam break maneuvers, aspect changes, or countermeasure logic before the heating becomes fatal. That is much stronger than saying it simply detects lasers. It classifies the threat and helps the jet react intelligently. And this is where the shield becomes layered rather than theatrical. A conductive composite skin would not only help with sensing and apertures, it could also contribute to EMI shielding, which matters because modern fighters are packed with sensitive electronics. Reviews of polymer nanocomposite shielding explain that EMI protection works through reflection, absorption, and multiple internal reflections. And recent stealth-focused materials literature specifically highlights graphene-based composites, conductive polymers, exenes, and related materials for protecting electronic systems while supporting stealth functions. But one balanced correction is important here. If we are talking specifically about laser weapons, their primary danger is optical and thermal damage, especially to surfaces and sensors. EMP-style electronic attack is more closely associated with high-power electromagnetic or microwave weapons, which are studied as a separate threat to electronics. So the most credible line for your script is this: Sweden's smart skin would not just harden the jet against laser heating, it could also help shield avionics against the broader electromagnetic chaos of future warfare. That sounds more professional, more believable, and honestly, more dangerous.
In the high north, geography punishes slow thinking. The Arctic is no longer a frozen blank space on a map. It is becoming a corridor of surveillance, deterrence, logistics, and strategic warning. NATO now openly says the Arctic and the high north are increasingly important for collective security, and by February 2026, it had launched Arctic Sentry to strengthen its presence there. Sweden's role is no longer theoretical. Stockholm confirmed it would contribute JAS-39 Gripen fighters to Arctic Sentry, while Reuters reported Swedish jets would help patrol skies around Iceland and Greenland as part of the mission. So if Sweden eventually fields a 6th-generation system shaped by advanced thermal materials, smart skins, and deeper electronic warfare integration, the real advantage would not just be national prestige, it would be relevance in one of NATO's most demanding theaters, where long distances, harsh weather, sparse infrastructure, and contested northern corridors reward aircraft that are resilient, networked, and hard to disable. That matters even more because Sweden's future air combat planning is not being framed as a lone heroic fighter story. Saab's official 2025 announcement says the future fighter work covers manned and unmanned solutions, a system of systems perspective, and technology development and demonstrators through 2027. Reporting in early 2026 also said Saab aims to fly a fighter-sized uncrewed demonstrator in 2027, ahead of a broader future fighter decision around 2030. That tells you something important. Sweden is thinking in architecture, not just airframes, and architecture is exactly where NATO interoperability lives. Gripen-E is already marketed by Saab as fully able to operate with Allied joint forces through common communication systems and network data links.
So, if Sweden proves useful new approaches in smart composites, heat management, sensing, or software-defined survivability, the likely NATO impact is not that allies suddenly copy a graphene jet overnight. It is that Swedish design logic starts influencing how allied next-generation aircraft think about survivability, networking, and modular integration. That is a more professional claim, and honestly, a more believable one. And this is where the future of air combat becomes clear. The old image of air superiority was built around speed, altitude, missiles, and who shot first. None of that disappears, but the center of gravity is shifting. NATO's own definition of electromagnetic warfare says military operations in every environment use the electromagnetic spectrum to create effects that support objectives and hinder the enemy's ability to do the same. Recent analysis from CSIS makes the same broader point. Air superiority is evolving into a mix of control of the electromagnetic spectrum, integration of kinetic and non-kinetic effects, and the use of autonomous systems. In other words, tomorrow's winning fighter may not be the one that simply carries the most missiles. It may be the one that sees first, classifies first, jams first, adapts first, and survives first. My opinion is that this is exactly why Sweden's future fighter story is so compelling. A smaller state cannot win by brute mass against bigger powers. It has to win by design intelligence. And if Sweden can combine low-signature thinking, thermal resilience, electronic warfare, and NATO-ready networking into one future combat system, then it will not just be building another interceptor. It will be helping to find what air superiority means after the missile age stops being enough. Thanks for watching.